So good morning. Today's lesson is probability in games. We're in the unit for probability. The bell ringer today is, what is the definition of a sample space of a multiple choice situation? So, for instance, this is looking at a situation. So perhaps maybe, what are the chances of a batter going up and hitting 3 singles in a row? And you just got to theoretically think about how that works. What is the sample space of a hitter going up to bat 3 times? So there are several different ways what will happen when he gets up to base. So he can go and get hit by a pitch. That's one. He can get struck out. Okay. That's 2. He can get a single, double, triple, or home run. So there's 6 opportunities when he goes up to base. Well, if he goes up there 3 times, that 6 is multiplied through 3 times. So 6 times 6 is 36. And then 6 times 36 is 216. So there are 216 possibilities when a batter goes up to the bat 3 times. So it's 6 to the 3rd power. In other words, so that's the sample space. We define the sample space as the total number of possible outcomes in a multiple choice situation. All right, so what is the sample space in this menu board? There are 4 different events, we call them. There's you order the type of bread you want on your sandwich, and the type of sandwich you want, then the side you want, then the drink you want. So there are 3 bread choices, 5 sandwich choices, 4 side choices, and 4 drink choices. And 3 times 5 times 4 times 4, there's 240 possible outcomes. That is the sample space, okay? Makes sense, right? So if we open the store today and each category item were equally likely, what is the probability the customer does not order Italian bread, any sandwich with fried pickles, and any drink? Okay. So this is review, obviously, from SAS 4, All-American Bistro, or All-American Breakfast, but this is a different kind of menu board. To find the probability of a specific series of events occurring, you find the probability of each individual event occurring and multiply through each of those probabilities to find the total probability. So the probability that it's not Italian bread is 2/3. And why do we know that? Because Italian bread is one of 3 choices, and the other 2 choices are white and wheat. So there's, out of 3, the probability of it happening is 2 out of 3 not happening. Sandwich, any sandwich is 5 out of 5, so it doesn't matter. Any side, we want fried pickles. There's 4 different possibilities in the side menu item, and you want fried pickles, that's 1 of 4. And finally, the drink, any drink, 4 out of 4. There's 4 opportunities, and we can choose any, so it's 4 out of 4. So we simply multiply through those 4 probabilities. 2/3 times 5 out of 5 times 1/4 times 4 out of 4 equals 40 out of 240, or 1/6, which can be 0.16 or 16%. Now, here's something I want you to understand. If you look here, on the test, you may get any one of these type of answers as the answer. You need to know how to translate into each one. To change 1/6 to 0.16, you just divide 6 into 1 and find the decimal version. And then when you want to change 0.16 to 16%, you simply want to move the decimal point 2 places to the right. All right, let's move on. Good things. Good things. We had a tennis match last night. We played Katy Pato, and we beat them 14 matches to 11 matches. So out of the 25 matches, we won more than they did. Please be sure to contact me if you got some good things you want to share. I would love to share them in this Google Classroom and let everybody know what you guys are enjoying. All right, so let's start with this new lesson. Victoria is playing a new video game in which the object is to find hidden treasures. To do so, she must travel through several levels, clashing with guards and watchdogs. In one part of the journey, Victoria must pass through 2 gates. Gate 1, then Gate 2, to get to the next level. The chance that gate 1 is open is 20%, and the chance that gate 2 is open is 30%. The game designer has programmed the gates so that the probability of both being open at the same time is 0.1. So draw a model of the situation to help you answer the following questions, and explain why you chose the particular type of model from among the various probability models. Now remember, we had 3 different types of probability models that we looked at: Venn diagrams, tree diagrams, and area models. So those are all graphical displays that describe probability. Let's look at some of them. Here's an example. That's a Venn diagram. Now we said that 20% of the time gate 1 is open and 20% of the time gate 2 is open, right? 10% of the time they're all open. So if you add the percentages together, gate 1 is open 10% of the time. Oh no, gate 2 is open 30% of the time. But they're open both at the same time 10% of the time. So you add the percentages together in the whole circle to find the total that gate 1 is open. Same thing here. And 10 plus 10 plus 20 plus 60 does equal 100%. So this is a good Venn diagram describing that particular situation. How about the tree diagram? Gate 1 is open. You have to go through it first to get to gate 2, 20% of the time, right? So if it's open, we'll go to gate 2, and it's open and closed half of the time, right? Is that true? I believe so. Let's see. When gate 1 is closed, we go there, and gate 2 is open 25% of the time and closed 75% of the time. What we have to do is determine how do we create both gates open at 10%. 0.2 times 0.5 is 0.1. So that's true. We're looking at the right answer. What is the percentage here? 0.2 times what equals 0.1? That's 0.5. That's how we carry that. On this one, both gates closed. We know that both gates are closed 60% of the time because we're looking at this Venn diagram. 0.8 times 0.75 is 60%. And this is how we calculated it. We're looking at this algebraic equation. What times 0.8 equals 0.6? Because we know that both are closed 60% of the time. Now, if we want to check and see if this is true, that 10% of the time both of them are open, or 20% of the time when gate 1 is closed, gate 2 is open. So 0.8 times 0.25 is 0.2. We know that because it's 1/3 of 0.75, and 0.8 times 0.75 is 0.6. All right, and the last one is an area model. Now, if you look, the hash marks going from the top right to the bottom left is when gate 1 is open, and the hash marks going from the top left to the bottom right shows when gate 2 is open. So 20% of the time, that's 20 out of 100 squares, it's a 10 by 10 block. 20 out of 100, gate 1 is open. Now 30 out of 100, gate 2 is open. So 1, 2, 3 times 10, that's 30. And notice that they coincide in this little 10% row, or 10 out of 100, when they're both open. And to prove it, neither gate is open 60% of the time. This is 1, 2, 3, 4, 5, 6 times 10, 60 blocks out of 100. So all 3 of these models help describe that particular situation. So what is the probability that both gates are open when Victoria reaches the part of the gaming? And explain your reasoning. The game designers programmed the gates so that both are concurrently open 10% of the time. Probability is shown in the intersection in this area model right here. See it? All right, what is the probability that only one gate is open when Victoria reaches this part of the game? So when do we show when only one gate is open? All right, when gate 1 is open, it's in this section right here, and gate 2 is not open, because if they were both open, it'd be in this intersection. So we know that at least 10% of the time, only one gate is open. Well, what if gate 1 is closed and gate 2 is open? And that's this right here. Gate 2 is open 30% of the time, but only 20% of the time is it open by itself, because 10% of the time it's both open. So we're going to add when gate 2 is open only 20%, to when gate 1 is open only 10%, and our answering is 30%. And of course, that's the answer I get. Probability of gate 1 being open is 20% part of the time. However, gate 2 is also open, so P only gate 1 open is 10%. Oh, is that what the question was? I apologize. I thought I was looking for when only one gate is open. Gate 1 is open 10% of the time. Gate 2 is open 20% of the time. We already did that. Neither gate is open 60% of the time. What is the probability that Victoria finds exactly one gate open? We just discussed that. Gate 1 is open and gate 2 is closed, or gate 1 is closed and gate 2 is open. The lighter shade area shows gate 1 only. Darker shade, gate 2 only. You add them together, 0.1 plus 0.2 is 30 or 30%, just like I had described. So Victoria encounters another challenge in the game. If she zaps a target in one try, she gets a chance to capture a bonus shield. But to capture the bonus shield, she must also hit a second target in one try. Victoria hits the target in one try on an average of 60% of the time. Let's draw a model of the situations to help answer questions 6 through 8. So, example for both situations. She misses 40% of the time. She zaps the first target 60% of the time. This is the situation in the first try. All right. This is both tries together. She misses the target the first time, it's 40% of the time. But out of the 60% of the time, she hits the target 60% of the time, still every try. So out of this 60% that's left, only 60% of it will get hit. So 0.6 times 0.6 is 36. And 36 from 60 is 24, and that's what's remaining. Hits first target, misses a second. Okay? So let's look into that. What's the probability she hits her first target? Explain your situation according to this probability. It's 60% of the time, 3 out of 5 times. How about, what is the probability she captures the bonus shield? That's when she hits both targets the first try. To capture the bonus shield, she hits the second target. She can't hit the second target only if she hits the first target. So the first target she hits 60% of the time, and she hits the second target 60% of the time. So 0.6 times 0.6 is 0.36. What is the probability she hits the first target and doesn't hit the second target? That's probably going to be, let's see, hit the first target. She has to hit the first target and miss the second target. Probability is that hitting the first target is 60% and missing the second target is 40%. 0.6 times 0.4 is 0.24 or 24%. So I'm going to launch you with this little meme. It's kind of funny, and anybody plays video games, you understand percentages of hit. It's very important to understand how well you can hit someone. But this is how controllers get broken. When you've got the gun aimed right at the alien's face and it's still only a 65% chance to hit, oh well. Anyway, that's it for the day. There is a lesson in the Google Classroom for this one. It is SAS 5, Probability in Games. Please do that lesson after you finish here. In the meantime, be blessed and be a blessing.